This tutorial video will provide you an example of how to apply multiple constraints with different steps within CES EduPack. The example we will look at is case study 5.14 from the Ashby textbook on energy efficient kiln walls. So here I've given you a picture of the schematic. So we have a kiln that's being used to heat up parts, and we have a heater, there's a temperature, there is insulation, and so we're specifically interested in this insulating material. If you go through and you read the case study, it provides you with the constraints and the objective function. And what we learn, what we can derive from those, is that there's going to be a maximum thermal diffusivity. This is going to make sure we don't have too thick of a wall thickness. And so this thermal diffusivity is A. Thermal diffusivity is based on other material parameters. So thermal diffusivity is defined as lambda, the thermal conductivity, divided by the specific heat capacity, Cp, and density, rho. And so this value of diffusivity needs to be less than 3 times 10 to the minus 6 meters squared per second. The second requirement is that the operating temperature must be at least 1,000 degrees Celsius. And then the third requirement is that we need to maximize our material index, which has been derived as being our thermal diffusivity to the 1/2 divided by lambda. I've also given you here the equation in case you wanted to use it that way, plugging in the value for A. So we'll open up CES EduPack, and you can see that I've already started this problem. So I've created the first graph where I've plotted my thermal conductivity on the y-axis and the thermal diffusivity on the x-axis. Remember, the x-axis values that I've given you here, this equation, this is our thermal diffusivity. And so again, if you right-click on the stage, you click on Edit Stage, this is where we can see that our y-axis and our x-axis, and I had gone in and used the advanced tool to define this equation. So the first thing that we're going to define here is we want this value, the thermal diffusivity, our x-axis needs to be no larger than 1 times 10 to the minus 6. So to do this in this plot, what I will do is I will draw a selection box. So I come up to the top, these little icons, we click the box selection, and I draw a box selecting all the materials that have a thermal conductivity that is lower than this. This only needs to be approximate. What we will then go do is we are going to go edit this. So to edit this, the box, we are going to right-click on the stage, go to Edit Stage, and now if you come up here to Selection, you can see the ranges. So we go from the smallest value of x, 3.28 times 10 to the minus 8, and we want to go up to 3 times 10 to the minus 6. So I'm just going to enter that in there. The y values, we just need to make sure it encompasses all of the materials. So I click OK. And so you can see now the materials that are colored are only going to be those that meet this selection. But remember, we have 2 other criteria that we need to do. The second criteria is that we need to have an operating temperature. So we need to get rid of any materials that can't sustain these high temperatures. So to do that, I'm coming over here into selection stages. So stage 1 is what we've just done. Now we're going to add a second stage. So I'm going to click on Limit. I want under Thermal Properties, we see that the maximum surface temperature, so that's how high of temperatures the material can sustain, this needs to be at least 1,000 degrees Celsius. So the maximum temperature needs to have a minimum of 1,000 degrees C. So if it's 1,200, the material has a surface temperature of 1,200, then it passes and it's going to be okay. We go up and we click Apply. And then the third part that we want to do is we want to apply our material index. So if we look at our plot, if we go back up here to stage 1, you can see that we have a selection box that's used, but we also want to put on a material index line. We can't put those on the same plot, so what I'm going to do is I'm going to right click, copy, and then I'm just going to paste the figure in again. And so now when I come down to stage 3, I'm going to delete my selection box, so I'm just going to click on it and click backspace, and now I can create my line. If we look at our material index, it turns out that the thermal conductivity, the lambda, versus A, this needs to have a slope of 1/2 or 0.5. So we enter that in and click OK. And like we've seen before, we select our line and we put it on. And so you can see here what's happening is it's eliminating any materials that don't meet those. But then what becomes interesting is you can see up here it's still leaving in all these large values. But what we can do is we can actually link these. And sometimes it'll automatically do this, but if it's not linked, what we do is we come up to these little buttons here, and I want to do result intersection. If I click on result intersection, it's going to gray out any of the materials that don't pass all 3 of our selection stages. So they need to pass stage 1, they need to pass stage 2, and they need to pass stage 3. And so we see that when we do that, I'll move my line down. You can see that when we do that, we end up with 7 materials total. Only 7 materials of the 100 in our database are going to pass. And so what I can do is I can draw my line. I can use this to select my material. We see that we get some options. We get our nickel superalloys, our nickel alloys. We get some zirconia, which is a technical ceramic. We get glass, ceramic, and brick. And so this can be used if we were only selecting the best material based on these 3 criteria. In this case, we would probably choose the nickel alloys, either the nickel-based superalloys or, I'll click here, the nickel chromium alloys. So you can see those overlap. Of course, they're not usually made of that. Usually a common material would be a certain type of refractory brick, but here we didn't include cost, and so that's sort of the basis of our selection. But you can see that if we choose these selection stages, it's going to, and we make sure over here to click result intersection, it's going to only show us the materials that pass all 3 stages. If I want to get rid of one of these stages and see, or just ignore it, I can just unclick it. And so you can see these are all the materials that we would have been able to select if we didn't have that maximum surface temperature of 1,000 degrees Celsius. You know, so if it didn't need to be that hot, we would get things like polymethyl methacrylate, a polymer. But those materials won't survive, and so we click on this, we include all of those, and you can see that is what we are left with. So using these selection stages to input multiple criteria is going to allow us to start solving more complicated problems using CES EduPack, where we don't just use one stage, but we use multiple stages.